Hello, this is Jennifer Martinez. In this video, we're going to go over orthogonal projections and the orthogonal decomposition theorem. But before we do, I would like to introduce the following definition: an orthogonal complement, which is denoted by W. This is a perpendicular sign, W perpendicular, or sometimes simply W perp. What is W perp? It is the set of all vectors that are orthogonal to W, where W is a subspace of Rn. Since W perpendicular is the set of all vectors that are orthogonal to W, we can write this in set notation. It's a set Z, a vector Z, where W is a subspace of Rn, and Z, that vector Z, is orthogonal to W. Here is a couple of properties. The first one, it is a vector X is in W perpendicular if and only if X is orthogonal to every vector that is in the set that spans W. To see property 1, let's look at a typical vector in W. So let's let W be the span of some vectors v1, v2 through some vp. I don't want to make it n because we're in Rn. And V is in W. So V in W has the form C1V1 plus C2V2, right? Plus CV, CPVP. So let's let X be orthogonal to every vector in this set that spans W. In other words, let's X be orthogonal to each Vj in the span. So from each Vj from J from 1 to P. And let's look at V dotted with X. So what would we have? Well, V is written as C1V1 plus C2V2 plus ... CPVP. And just dot that with X. And from the properties of inner products, we know that we can distribute this X to be C1, V1 dotted with X, plus C2, V2 dotted with X, and so forth. And since X was orthogonal to each Vj, we know that each one of these is 0. So this whole thing is 0. So this is true if and only if X is orthogonal to each vector, we'll call it V, in W. So by definition of the complement, orthogonal complement, that means that X is in W perpendicular. So that was the proof of 1. 2 says that W perpendicular is a subspace of Rn. So let's go ahead and show that. So to show that W perpendicular is a subspace, I want to see if that subspace is closed under addition. So I'm going to let Z1 and Z2 be in W perpendicular. And if you remember by the definition of W perpendicular, that means that, well, any W perpendicular is any vector where W is a subspace of Rn and Z is an orthogonal to W. So we know that Z is orthogonal, or Z1 and Z2 are orthogonal to W. Which means for any U in W, we know that Z1 dotted with U equals 0 and Z2 dotted with U is also 0. So let's look at Z1 plus Z2 dotted with U. And that is going to be equal to the same thing as Z1 dotted with U plus Z2 dotted with U. And therefore the whole thing is 0 since each one is 0. So now let's see if it's closed under scalar multiplication. Is C times Z1 in W complement? So I'm going to look at CZ1 dotted with my same U. And we know that that is the same as C times Z1 dotted with U, which we know is 0 because Z1 is orthogonal to any vector in W. So it is closed under scalar multiplication. And the 0 vector is in there, since 0 is orthogonal to every vector in W. We know that 0 is in W perpendicular, and that does it. We know that W perpendicular is a subspace. To prepare for the next theorem, we're going to look at this example. Let's look at a set U1 through U5, and this set is going to be an orthogonal basis for R5, and let Y be a linear combination of C1U1 plus ... to C5U5. Let's consider a subspace W of the span of just two of these, U1 and U2. We're going to write Y as the sum of a vector Z1 in W and another vector Z2 in W complement. So how I'm going to do this is I'm going to let Y equal Z1 plus Z2, where Z1 is going to be the linear combination of U1 and U2, and Z2 is going to be a linear combination of U3, U4, and U5. So therefore, Z1 is in the span of U1, U2, which by the way is W, and Z2 is in the span of U3, U4, and U5. So all we need to show is that Z2 is in the complement of W. So I'm going to look at Z2 dotted with the things in W. So I'm going to look at Z2 dotted with U1. So here is Z2. We're going to dot that with U2, and we're going to get 0 since we let U1 through U5 be an orthogonal basis for R5. That means each vector in here dotted with another vector, any vector besides itself, is 0. And each one of these, therefore, is 0. U1 is orthogonal to U3, U4, and U5. And by the same similar process, Z2 dotted with U2 also is 0. And here it is. Here's Z2 dotted with U2. Each one of these is 0. So by our first property above, let's look at that. If X is orthogonal to every vector in the set that spans W, we know that X is in that complement. So we have it. Z2 is orthogonal to every vector in the span of W. So Z2 is in the complement. The next theorem is going to show that this composition can be computed without having an orthogonal basis for Rn. It is enough to have an orthogonal basis only for a subspace W. And we're going to show that in the next video. So stay in tune.